I want to continue and talk about random sets and their properties. And so far we related between regular random variables and random sets. First, constructing random sets using regular random variables, and then starting from a random set and then selecting a specific random variable out of the random set. Okay, so now we want to see if there is something that relates again the selections to the random sets, and to some extent we want to see if there is any equivalent of the probability distribution that is associated with a regular random variable, and something which will be called capacity and containment functionals for random sets. Okay, so let's remind ourselves that if we have a regular random variable x, okay, the one that goes from omega to Rd, okay, for any a in the Borel set of Rd, okay, we can write p of x of a, or px of a, okay, to be equal to the probability, and that's the probability from the probability space, of the set x minus 1 of a. Okay, so this is well defined because x minus 1 of a is a subset or a member, sorry, of the sigma algebra, so we can evaluate the probability of that set. Okay, so this is a probability distribution or a probability measure induced by the random set. So let's see if we can find some kind of an equivalent when we talk about random sets. Let's try to find an equivalent for the probability distribution or the probability measure for random variable x for the random set. Okay, so let's see the following definition. Let x, capital X, be a random set. Okay, defined on this random on this probability space. Okay, let t, the following functional t that we'll call capacity functional t sub x for a be the probability that x intersection with a, okay, intersection with a here is non-empty. Okay, so it intersects with a in a non-empty way. Okay, so this is the capacity functional. Okay, so let be the capacity functional of x. Okay, and similarly let cx of a, containment functional, be equal to the probability that x is contained in a, okay, be the containment functional. Okay, and we are going to define this, okay, for any a which is compact. Okay, so let me edit like this. Okay, so this is for any a compact. Okay, compact in Rd. Okay, first thing that you can observe is that for any compact A, okay, we can see from the definition here that C, okay, Cx of A is less or equal to Tx of A. Okay? So let me remind ourselves the first example for the random set. So let's look or see again the example. Okay. Where X is just this singleton random set, okay, based on a random variable small x. Okay. What is T X of any compact set A? Okay, so let's work with the definition. It's the probability that X, which is just this small x, okay, intersects with A, okay, and that's just equal to the probability that X is in A. That's the only way that can happen, which is again similar to the, okay, similar to what's written here. Okay, so it's another way to write it is X, okay, contained in A. That's the same thing, which is Cx of A. Okay, so they now it's equality. But more than that, if you look at the definition, okay, here, okay, here the x is in A, or x like this is in A, okay, it's going to also, and you can check that, it's also equal to Px of A, okay, because it says that here are all the omegas, okay, for which x of omega is inside A, okay, that's the inverse of A, like that. So this is this case. So if you have a regular random variable that you just turn it into a random set, the capacity functional, the containment functional, and the distribution function are exactly the same. Okay. Let's see another relationship between the capacity and the containment functional. So let A be a compact set. Okay, let's write what is the capacity functional. Tx of A, okay, is the probability that X intersects with A. Okay, so this means if we write here is a set A, okay, and we take X, okay, for X to intersect, and X will be random, A is fixed, it means that it can't be that X, all of X is contained inside the complement of A. So this is equal to 1 minus the probability that X is contained in AC, okay, which is 1 minus the capacity of AC. Okay, so the relationship between the containment and the capacity is that the capacity functional is equal to 1 minus the containment functional of the complement. After having these two results, and especially inspired by this result that relates the probability distribution of X with the capacity and containment, what if X is not this simple random set, but a regular or general random set? Okay, so let X be a random set. Okay, and let cell X be the selection set of X. Okay, can I say something about the member of the selection, or a selection from X? And here comes a very fundamental, very important result in random set theory, and this is called Arnstein's lemma, sometimes called Arnstein inequalities. And I will give a version of it which is not the most precise one, in the sense that you have to take care of are the random variable and random set realized on the same probability space and so on. So let me just give the simplified version of the Artin lemma, which says the following. A random variable x, okay, is a selection from the random set capital X, if and only if, and that's the strength of this result, okay, the probability X of any set A, any compact set A, is less than or equal to the capacity functional X Tx of A. Okay, and equivalently, okay, it's another way to say the same claim, is that Px of A is bigger or equal to the containment functional evaluated at A. Okay, and then you can say that and see from the result for the equivalence between Tx of A and the Cx of A complement why this will happen. But this has to be true, okay, if and only if either this or equivalently the second one happens for all A compact. Okay? And then, of course, here it's satisfied. It's the simple one to show. But Artin lemma says that a random variable will be a selection of a random set if and only if this inequality, or equivalently the other inequality, are satisfied for every compact set A. Okay? And that's a very important result. Thank you for watching.